Hi, in this video we are going to talk about the kinetics of reversible reactions. We have already spoken about irreversible reactions and now it's time to address reversible ones. So, uh, in practical or in real life situations, no reactions ever really reach the completion point, and we can consider many reactions to be irreversible because of the large value of the equilibrium constant. Okay, now this equilibrium constant is the ratio of the concentrations raised to the stoichiometric coefficients. Okay, we'll shortly see this when I write it up. Now, but there are situations where complete conversions cannot be assumed. Okay, so that leads to reversible reactions. And the simplest case we'll consider, that is the unimolecular type reversible reaction, and we'll see how to draw its kinetics out. So let us consider the reaction as A gives R in a reversible manner, where the rate of forward reaction is K1 and rate of backward reaction is K2, and Kc is our equilibrium constant. Okay, so at equilibrium conditions, the ratio of the concentrations of the components raised to the stoichiometric coefficients is what we obtain as the equilibrium constant. So I'm writing the sign small e as the subscript to understand that these are all in equilibrium conditions. Okay, and the ratio of the product concentration to the reactant concentration raised to their respective stoichiometric coefficients, that is your equilibrium constant. So this is the reaction that we are going to study now. It is reversible, so it goes on in both ways, and at equilibrium point the dca dt will become 0. Okay, so the rate of forward and backward reactions will become equal. Therefore, I am writing that in terms of the reactant, the rate equation will be equivalent to 0. That gives your equilibrium condition. Now, let's start with the analysis. If we consider the integral analysis, then how will we get the expressions? So, first things, considering the concentration ratio M, that is Cr0 by Ca0. This is the initial concentration ratio, okay, in which the reactant as well as the product are present. Then we can write that dcr dt equals to minus dca dt. This is obvious because it's a reversible reaction, so the rate of forward reaction is exactly negative of the rate of backward reaction. So we write in this manner, equals to Ca0 to dxa dt. So this is in terms of the conversion of A, that is equivalent to K1Ca minus K2Cr. Okay, now this you can further simplify and write as K1 into Ca0 minus Ca0xa, and the second term is minus K2 into mCa0 plus Ca0xa. Okay, so this is like we are going towards production of R if you are considering the conversion term for R. Okay, So there is a plus sign over here and not minus. Now this is the overall rate equation for the reversible reaction that we have. Now if we consider that at equilibrium this dCA dt will go to 0, okay, dCA dt goes to 0. So practically this entire expression is equivalent to 0, okay. Therefore we will find the fractional conversion of A. So in case of a reversible reaction we cannot achieve complete conversion at all, okay, but in this case we will now consider fractional conversion of A at the equilibrium conditions. That is given as Kc equals to CRe by CAE, like I wrote earlier, and this is equivalent to M plus XAE by 1 minus XAE. So that is obtained if we set that dCA dt equals to 0, okay, and the equilibrium constant Kc is equivalent to K1 by K2, okay. If you combine these equations, this main rate equation and the expressions that we have obtained for the fractional conversion and the equilibrium constant, then you can also get the expression as dxa dt equals to k1 multiplied by m plus 1 multiplied by xae minus xa divided by m plus xae. So you are now relating the fractional conversion of A to the conversion of A as a whole, okay. So this is another way that you can represent. Now this if you are like going to find the integrated form of this equation, this again is a rate equation, but if you find the integrated form of it, then you will get something like, let me directly write the integrated form for you, minus ln 1 minus xa by xae equals to minus ln ca minus cae by ca0 minus cae equals to m plus 1 by m plus xae multiplied by k1t, okay. Now one interesting thing that you can note here, if you put CAE equals to 0 and rather I should say or XAE equals to 1, then the expression becomes exactly like the first order reversible reactions integrated form. Okay, so if you just put Ca equals to 0, you will get minus ln Ca by Ca naught, and Xa equals to 0, then you will get K1t. Okay, so m plus 1 by m plus 1, so you will just have K1t over here, and this is the irreversible first order kinetics. Okay, so you can also say that the reversible reaction is actually a special case for the reversible reaction, right? And so this is the integrated form for the final integral analysis that you can directly use, where you can fit in your experimental data. So the idea is that if you graphically plot this, Let me show you the graphical understanding. So if you graphically plot, on your x-axis you have t, and on your y-axis let's say you have minus ln 1 minus xa by xae, or the other term, or minus ln ca minus cae by ca0 minus cae. Okay, then you will get a straight line starting from 0 whose slope is given as k1 multiplied by m plus 1 by m plus xae. Okay, this is how you can draw out the kinetics for first order reversible reactions. Okay, it involves integrations. Now if you do a similar thing for second order reversible reactions, let me show you the cases for second order reversible reactions. So here I am considering bimolecular second order reaction types. Okay, so this can be of the 4 different format that I am going to write down. The first format is like A plus B reversibly gives R plus S. This is one form. Another form is 2A reversibly gives R plus S. The third form is 2A reversibly gives 2R. The other form is A plus B reversibly gives 2R. Okay, so these are the 4 forms. Now for all the cases, if you consider that Ca0 equals to Cb0 and Cr0 equals to Cs0 equals to 0, that means at the initial state no products are present, then the integrated form for all of these 4 equations will become the same. I will write the integrated form directly. I am not writing the rate equations here. So it will be ln xae minus 2xae minus 1 multiplied by xa divided by xae minus xa equals to 2k1 multiplied by 1 minus xae minus 1 multiplied by ca0t. Okay, this will be the integrated rate form for the second order reversible reactions. Okay, now if you want to make a plot, obviously this is your y term, so this will be on the y-axis. You have t on the x-axis, and this becomes your slope. So this again is fairly simple for testing the experimental data. Now the catch is that if your experimental data does not fit for the integrated forms of second order reversible and first order reversible reactions, then obviously you have to consider reversible reactions in general. Okay, but obtaining that by integral analysis becomes very complicated, because now you have a higher order and a larger number of components involved. So to address reversible reactions in general, let me write this down. To address reversible reactions in general, we use the differential analysis method. So far, we have been talking about integral analysis method, but for addressing reversible reactions in general, when it is neither first order nor second order, then we will use differential analysis method, and that is in itself a totally different topic altogether. So that is it for this video. I have discussed the first order reversible reactions and second order reversible reactions. Okay, thank you.